Okay, kids, we're back. Now, what you see on the board behind me is some data and an equation. Yeah, we'll get to that. That's called the conductivity equation, the heat conduction equation. Now, what we're going to talk about real quick here, though, is today. I mean it real quick. I know. You always say it can be real quick. It's not like 20 minutes. Okay, calm down, Billy. Calm down. This is going to be fast. So there are three different kinds of heat transfers. Three different kinds of heat transfers. You got to know them. Here they are, in no particular order of importance. You've got one called conduction. Conduction. You know what conduction is? No, not that conduction. Stop it. You said I was going to be fast. Sorry, I can't help myself. I can't help it. Now, conduction. Conduction is one kind. Conduction. You need heat to move through something. So you got to have something. You have some material, some stuff. I don't know, name a material. Concrete, that works. Copper, that works. Glass, that works. Okay? Heat goes through materials, that's conduction. Heat flowing through a material, through it. So when I took my aluminum spoon and put it in the roaring fire when I was in the Boy Scouts, that was conduction. It was the heat was going through the material into my hand. Got it? Conduction. Through. That's the key word. Through stuff. All right. There's another one called convection. Convection is based on density differences. Things will move, groove, shake, and bake. You know that hot air always rises. Yes, you do. You know that. You know that hot air rises. And so like baseboard heating, you put baseboard heating, it's effective. It's more effective than putting heat coming in through a vent through the ceiling. And because what happens is you put the heat down below and it rises, displaces the cold air, causing the cold air to fall. Okay, hot air rises, cold air will sink. Heating up that air, and you get what's called a convection current. So a convection current, okay, convection is the mixing of different densities. It doesn't have to be air, it can be fluids too. There are convection currents in the ocean, volcanic activity down below heats up the water, that water less dense, so convection currents, okay? That is caused by density differences. So there's convection ovens. They heat one part of the oven, it causes the air to cook. It cooks better because you get the air moving, going around the food. Density differences. Okay, then the third kind of heat transfer, talking about moving heat from one part to another, is radiation. You mean the bad stuff at Chernobyl? No, that's actually different. Well, I mean, that's not true. I mean, gamma radiation is radiation. Okay, it's radiation. We're talking about radiation, and we're talking about the stuff from the sun. Okay, and then that can go through space. That's electromagnetic radiation, the electromagnetic spectrum. We talked about that. Yes, we have. You learned about that. I would hope at some point. I mean, if you're my college physics class, we had learned about that already. Okay, if you're not my college physics class, then we haven't learned about that yet. But don't you just wait. You just wait. So, anyways, electromagnetic radiation. The biggest source of that ball in the sky, which I haven't seen a lot lately. It's been raining an awful lot. Bad rainy summer. But we get that ball in the sky. Now that heat, when you go outside and you stand in the sun, you feel warmer. You're receiving radiant energy. And that's energy in the form of electromagnetism that can travel through space. Space means no material, a vacuum. So radiation is EMS, electromagnetic spectrum, and that can be infrared radiation. It can be, that's heat radiation. Actually, you and I give off anything that's living gives off the infrared radiation, radiating energy out into the environment. You can't see it. You can't see my heat coming off my body here, but it is. I am just like on fire. I'm just giving off so much radiation. You can't see it unless you're the predator. If you're the predator, you can see it because he sees infrared. Remember the predator? Boom. He can spot you. Unless you're on Schwarzenegger and you put mud all over you and you block the infrared because you're smart, you're like Arnold. I don't know. Get through the chopper. Yeah, that one. Okay. I'm sorry. I'm going off on a tangent again. Okay, let's get back. Refocus. So radiation is another form, and this can travel through space, which makes it unique. These can't. You need stuff to have a density difference, and there's no stuff in space. So you don't get this in space. You need stuff to travel through stuff. I mean, that makes sense, right? And so if there's no stuff, you can't have that one. This one can travel, can go, which is a good thing for you and I. Otherwise, we'd be in big trouble if the sun couldn't send its energy to us. And travel through space. Okay, those are the three basic ways that heat can be transferred from one spot to another. All right, and sometimes there's more than one just going on. Sometimes there's a couple of these things in combination working together to transfer heat. Let's focus on this one right here. The equation that I have over here is the conduction equation. Conduction. Now, if we're going to do conduction, we need some stuff. We need some stuff for the heat to travel through. And this is a rate of transfer. Conduction means we're going to put energy, put heat through a material, okay, at a particular rate. So it's joules per second. You know, how many joules per second are we transferring through the material? It's a rate. And when you put anything over time, it's a rate value. And then we're going to need some thinking. What are these things? What's that K? Okay, that's the stuff. The stuff that dreams are made of. Yeah, physics is made of dreams of good stuff. That K value refers to the material that you're transferring the heat through. So K is going to be different for different stuffs. Now, if you were talking about copper, okay, it's going to have a different heat transfer rate than aluminum, different heat transfer rate than lead, than glass. Okay, and that's my example up here. I said a window, okay, here's my example. I'm going to use this equation. A window, 2 meters by 1.5 meters, and it's 3 millimeters thick. So we got this window. So, you know, it's a pretty big window, 2-meter window. It's good size. Oh, it's about that size. Good size window. So it's 2 meters by 3 meters. 1.5 meters. And it's 0.3, actually I said it's 0.003, because that's 3 millimeters. Gotta have that in meters, okay? These are, no, not gonna work when you have different units. So let's put that in meters. 3 millimeters thick is about yay thick. So, but we need that in meters. So 0.003 meters. Okay, moved it over 3 times. And so it's gonna look kind of like this. Here's your window. Okay. And that part of it is the 0.003 meters. All right, so what we're going to do is windows are a source of heat loss for buildings. A single pane window, like this, if it's a single pane window, you're going to get a lot of heat loss through it because heat goes through glass relatively readily. Now, if you have double pane glass or even triple pane glass, and you have something in between, actually dry air is a pretty good insulator. Okay, pretty good heat insulator, so dry air. Sometimes triple pane windows, double pane windows have argon in between, also a very good insulator. It doesn't allow heat to travel through as fast. If you have a single pane window, though, that is not going to be very good for your energy bill. Okay, you're going to have a lot of heat transferring through that. And so let's figure out what we have for heat flow here. So this is glass. So that K value, I'd have to look up for glass. In fact, I have a book right here. I mean, I don't have these things memorized off the top of my head. Actually, glass I do, but the rest of them I don't know. So you find a book, or you look it up online, go Google it. You kids are the Google generation, okay? Google it, for crying out loud. You can Google everything. Okay? So like in this book here, we have a table here of those different K values. Yeah, all different things. And so the K value for glass is 0.84. So that's going to be 0.84. I'm going to write that down for now. 0.84. And the units are joules, seconds, and meters, and degrees Celsius. And those are the units that are actually going to end up canceling out in this equation. And it's going to give me joules per second. So I'm going to end up with a rate of joules per second because the meters, the area here, this is going to be in meters, and the degrees Celsius is going to cancel out as well. And so this is going to be an area here. Area is meters squared, and it's going to be over length, which is meters. So meters squared over meters, we cancel one of the meters out, we get meters, and that meter in the unit cancels. I'll show you, okay. So let's figure out what the heat transfer rate, how many joules per second we'd be losing through this piece of glass, this window pane, single window pane. Okay, what do we got? Okay, let's use the equation. So the amount of joules per segunda grande, which is Spanish for big second, is equal to K, which is 0.84 joules over seconds, meters, degrees Celsius. I'm putting the units in just to show you how the units are going to work. Typically when I do a problem, I know the units are going to work, so I just put the numbers in and get her done. But let's see. So that is my K value. Oh, the area. Because what's the area of the window? The area of the window, rectangle, 2 times 1.5. Let me put that in there. 2 times 1.5 is going to be 3. Okay, so I'm just doing the math on that for you, okay? Get a calculator, check it. But 2 times 1.5 is 3. So on top we have 3 square meters. All right. Then Now we want to know the change of time. Change of time. Just change in temperature. Delta T, change temperature. You're not going to get a heat flow unless you've got a temperature gradient, a temperature change. So inside the window, outside the window. That's why I put the 15 and 12 here. So maybe inside is 15 degrees, outside is 12 degrees, okay? It could be the other way around, doesn't matter. But you have a temperature change. If you have the same temperature inside and outside a window, you'll get no heat flow. But if you have a temperature difference, like they say, it's warm inside, nice toasty warm inside, it's 70 degrees inside the house, but outside it's like 5 degrees. That's not going to be good. We're going to lose a lot of energy. That's a big temperature difference. The bigger the temperature difference, you see it. Yes, you do. Yes, you do. That is on top of the fraction. That's on top of the fraction. You make that big, you're going to get a lot of heat flow. Okay? Big, a lot of heat flow. It's the same thing with your body. If you jump into an ocean off the Titanic just for kicks and giggles for fun, yay, I want to go swimming around the iceberg. You do that. Okay, your body is 98.6-ish. Mine's actually runs at 90. We learned this during COVID, I think. We all kind of know what our body temperature is now. Mine is like 97.6. I'm like cold-blooded, man. I'm cold-hearted. Where was I? Yeah, you jump into the ocean. You're 98.6. Well, the ocean might be, I don't know, maybe 32.5. Anyways, that's a huge, huge temperature difference between you and the ocean. You're going to get some serious flowage there. The bigger the temperature difference, the faster and more flow you have. So yeah, you're going to go into hypothermia within a couple of minutes. Dead. Like Leonardo DiCaprio. You saw the movie, the Titanic. He was on the Titanic. He should have gotten on the thing, and he should have, but she wouldn't let him. No, you stay up, Jack, you stay up. And she didn't actually say that, but whatever. Okay, spoiler alert. Turn this off if you don't want to hear a spoiler alert. Jack dies. He makes a very good corpse. That was his best acting I've ever seen him do. Dead. Okay, turn it back on. Okay, I didn't want to spoil a movie for you. And oh, by the way, the boat sinks. Boat sinks. Titanic. Where are we? Oh, temperature difference. So here we have a temperature difference. So heat will flow. It's not going to flow too fast. It's not a really big temperature gradient here, but it's still going to flow. So I want the change in temperature in degrees Celsius. So that is 3 degrees Celsius. All right, let's see. Over L. The L can be under this one, or under the whole thing. It doesn't matter. Mathematically, you're going to multiply and divide by L, so it's irrelevant where you put the L, as long as it's on the bottom. And so we put this whole thing over L. Now L, that is the length that the heat is flowing through. In other words, the thickness, in this case, the thickness of the glass. How far is the heat flowing through? Now, if it was like a pipe, like if you had a copper pipe, it would be the length of the pipe, heat flowing through the pipe. But here we got heat flowing through the window, thin window. So we put the thickness of the window down here, 0.003 meters. All right, now what ends up happening, I just want to show you the units. Degrees Celsius cancel with this. This square meter cancels out with that. So then I have meter and meter here. So that cancels, and boom, joules per second, joules per second. Oh, we're so good. And then we're going to do the math on this and see what we get. Okay, well, I'm going back to my crappy calculator, and hopefully it'll be in the right units. It is still in the right units. Okay, so here we go. Let's do it. 0.84 times 3 times 3 equals, divided by 0.003 equals. I got 2520. 2520. So Q over T equals 2520 joules per second. That's what that means. So this window, that's a big window. You're going to be losing 2,500 joules per second. Per second. Okay, start adding those seconds up. Joules adds up. Now we know joules is a small unit, but when you start pumping this out for hour after hour after hour, you are losing a crap. That's going to end up to be a crap ton of heat energy going out your window. And this isn't even a very big temperature gradient. Look at that temperature gradient. It's only 3 degrees. It's only 3 degrees. What if it was like 100 inside your house and 0 outside the house? Wow. What would happen? This becomes 100. 100 is 33 times greater. So if it was 100 inside your house, which I hope it's not, but and it was 0 outside, this would be multiplied by 33. Times 33? Yeah, let's look at this. Look at this. This is 83,000 joules per second. Try that on your energy bill. Yeah, you're not going to be happy. okay? Point is, what is my point? Well, my point I was going to make about the window is single pane, not good. You want double pane and you want air in between or argon. You want some sweet insulating, highly graded windows to keep your energy bills down, okay? Because glass allows a lot of flowage through it. It has a high K value, all right, high K value. All right, so are there things higher than glass? Yeah, of course there's things higher than glass. I was looking on this thing right, like silver is 420. Whoa! Glass is 0.84, silver 4. Aluminum, remember the aluminum ladle I keep telling you about? It's stuck in the fire. Okay, that one is on here. Aluminum is 300, no, lies, 200. 200. So 200. And I had a, you know, I'm warm. Okay? And so the fire, well, the fire's a lot warmer, a lot warmer than I am. So the fire, I don't know, 1,000 degrees, it wouldn't be 1,000 degrees. It was just firewood, so it would be less than that. But anyway, the point is it's a huge temperature gradient. And aluminum is a big value here, 200. You're going to get a sweet amount of flowage going to that hand. And can't hold on to it very long because it's very quick with the amount of heat energy transfer. Okay, that is a problem, an example problem using the conduction equation. All right, let's see. Let's see. I think that'll do it for this video. I think we've got it. We got our 3 energy transfer mechanisms, and we did an example using the conduction equation. Like that equation. Like it. All right. Okay. I think you get the hint, and we'll talk to you soon.